Okay, so question 5, good old Harbour process comes back to haunt you, and the first thing it wants is just the expression for Kc. So here's the reaction. Remember, the stuff on the right goes on the top. So Kc equals NH3 square brackets to show concentration, and because there's 2 ammonias, remember you have to square it. So whatever those numbers are, you raise it to those powers. Left hand side we've got N2, again square brackets to show concentration, and H2 cubed, because there's 3 of them. So that's your expression. And the units, if you figure it out, you've got moles per dm cubed squared on the top, moles per dm cubed to the 4th on the bottom, so it's moles per dm cubed to the -2, moles to the -2 dm to the 6th. If you're not comfortable doing it algebraically like that, the cheat recipe is that you add up the number of things on the right and subtract the number of things on the left and call that number x. Okay, so moles on the right minus moles on the left is equal to x, and the units of Kc are moles to the x dm to the -3x. So in this case x is 2 minus 4 is -2, so moles to the -2 dm to the 6th is the answer. Okay, so make sure you can do those. Then we get to the calculation, and it's fairly straightforward, except that it doesn't give you any guidance really, so you've just got to make your own way through it, but there's nothing too hard about that. There's no major tricks in it. The first thing is to recognise that we need the concentrations of these substances, and what we're actually given is numbers of moles. So as a starting point, we need to work out the concentration of nitrogen and the concentration of hydrogen. So the concentration of nitrogen is moles over volume in dm cubed, which from the information you're given is 7.2 moles divided by the volume is 6.0 dm cubed, which is 1.2 moles per dm cubed. Same for the hydrogen, same recipe, but this time we've got 12 moles in our 6.0 dm cubed, so that's 2.0 moles per dm cubed. Okay, so now we've got the numbers. It gives us the value for Kc, which is 8.00 times 10 to the -2, and we now need to just rearrange this expression so that we can solve for the ammonia concentration. So remember, the things on the bottom need to be moved over to the other side, and they move diagonally across like that, so we can get the Kc times N2 times H2 cubed is equal to NH3 squared. Okay, just moving them across like that, and then if we take the square root of both sides, we get that the square root of that lot is just equal to the ammonia concentration, and that's how we're going to get to the answer. So we plug the numbers into that, and we get the square root of 8.00 times 10 to the -3 times 1.2 times 2.0 cubed. So you multiply them all together and then find the square root, and you should find that that comes to 0.876 moles per dm cubed is the ammonia concentration. But then that's not what it asked for. It wanted the actual amount in moles. So the final step is to remember that moles is equal to concentration times volume in dm cubed. So we've got to multiply that number by 6, because remember our volume was 6 dm cubed. So that's 0.876 times 6, which is 5.3 once it's rounded off to 2 significant figures. 5.3 moles is your answer. Okay, so that's, as I say, fairly standard calculation, but not very much help. So you had to just keep your head and see your way through all those steps. Okay, so now usually when you've done a calculation like that one, what you should expect next is some kind of discussion based on Le Chatelier's principle, and that's what you get in the next part, which the first one is quite straightforward. So we need to restore that equation. And so it asks you to explain why, if you increase the pressure, double the pressure, the equilibrium shifts to the right and you get more ammonia. So to get the marks, you first of all explain that the equilibrium shifts to the right in order to oppose the pressure increase. So remember to try and use that language of opposing whatever the change is. So it shifts to the right to oppose the pressure increase. And then there's got to be a because. How is that opposing the pressure increase? Well, it's because there are fewer moles of gas on the right hand side. And you needed to spell that out to get the marks. So it shifts to the right to oppose the change because there are fewer moles of gas on the right hand side. And that's how it opposes it. Now part 2 is much trickier. It asks you to explain in terms of Kc why that happens. So let's just restore our Kc expression that we had before. N2, that should be. And the first point to make is that Kc doesn't change when you change the pressure. Okay, that's very important. That the only thing, remember, that can change the value of Kc is a change in the temperature. So the first point to make is Kc is the same. And then you say, well, okay, if it didn't shift, that's the way to think about it. If it didn't shift, what would be the consequences of doubling the pressure? So we double the concentrations because we got the same number of moles in half the volume. If there were no shift in the equilibrium, we'd simply double each of these concentrations. So if there's no change, or no shift in the equilibrium, what will happen to this expression? Well, the top line will increase not just by a factor of 2, but by a factor of 4, because it's concentration squared. So if you double the concentration, top line increases by 2 squared. So top line will increase times 2 squared, in other words, times 4. But the bottom line, you've got concentration to the power 4 there. So if you double the pressure, the concentration, or the bottom line, will increase by a factor of 2 to the power 4. So bottom line will increase times 2 to the power 4. So the overall expression will give a value, okay, which changes by a factor of, well, 2 squared is 4, 2 to the power 4 is 16. So it changes by a factor of 4/16, which is, it's a quarter of what it should be. And that's the point, that it therefore has to shift, otherwise the concentrations aren't consistent with Kc. And you can see that in order to come back to its original value, if it's now dropped to a quarter of its original value, the reaction has to proceed in the forward direction to increase the value of the top line. Okay, so you say therefore proceeds in the forward direction to increase the ammonia concentration until it's consistent with Kc again. So this is quite an important kind of question, because it's harder to get your head around, but we started from the idea that from that expression we can look at what would happen just as a result of changing the pressure if there were no change in equilibrium. And you can see that because the top line is concentration squared but the bottom line is concentration to the fourth, that you get a different effect on the two lines. And when we worked it out, the overall effect is that this ratio would drop to a quarter of its original value, and therefore the reaction has to proceed in the forward direction to make more of the stuff on the top line to restore it to its equilibrium concentrations. So try and get your head around that one. That's, you know, at the top end of the difficulty range for these kind of questions. So it's not the end of the world if you're still a bit shaky on that, but it's definitely worth thinking about. Okay, back to more straightforward things. Now we've just got to propose an equation for the reaction of methane and steam to produce hydrogen. There are various possible equations for this one. And so, you know, don't spend hours trying to figure out which one is right. If they don't give you lots of detail as to what the products are, then, you know, there may be more than one possibility. So we just know that we've got methane plus steam turns into something plus hydrogen, and it doesn't tell us what the something is. So the most obvious thing is to say, well, if that carbon reacts with that oxygen, we can make carbon monoxide, and that just leaves all the hydrogens, 6 hydrogen atoms there. So 3H2 would do nicely. Remember, with equations, always check if it wants state symbols, but it doesn't say that here, so you don't need them. Then it says, okay, that's one way to make hydrogen. How could we do it in the future if that ceases to be viable? The main alternative that's currently considered is electrolysis of water. Okay, if you pass an electric current through water, it breaks up into hydrogen and oxygen, and that's the one that may become more important. There are others, but they weren't allowed on the mark scheme, so don't go for the way out. That's the one that's most likely to be used. And then over onto the next page, we're into entropy and free energy. Now, so let's have a look at this one. So what we're being asked to do is to show that this reaction, the formation of ammonia, is feasible. And remember, to decide that, we need to use this relationship. Delta G is delta H minus T delta S. We've got to compute delta G, and then what you say is that if delta G is negative, then the reaction is feasible. If it's positive, then it's not feasible. So that's what we're aiming to show, is that delta G is negative. So we're given delta H, but we've got to find delta S. And we can do that from the molar entropies. So from your equation, which, remember, write it up again, is this. Delta S for that reaction is equal to the molar entropies of what you've actually got at the end, minus the entropy that you've lost, because these substances aren't there anymore. So it's plus 2 times the molar entropy of ammonia, so 2 times 192, because you've got 2 moles of ammonia at the end, and then take away the entropy that you lost. So we lost a mole of nitrogen, so minus 191, and we lost 191, and we lost 3 moles of hydrogen, so 3 times 131, and if you work that out, that comes to minus 200, and you can get the units from the table at joules per Kelvin per mole. Okay, so now we've got delta S, we've got delta H, and T is remember, the temperature in Kelvin. So T is equal to the temperature in degrees C plus 273. You have to remember that number and what you do with it. 273 is equal to 0 degrees C. So whatever your degree C temperature is, you have to add 273 onto it to get Kelvin. So temperature is 25 plus 273, which is 298 K. So then we can compute delta G. Delta H, we're told, is minus 92. And then it's minus 298 times, and we've got to be careful with delta S for 2 reasons. First of all, remember that because delta G and delta H are going to be in kilojoules per mole, then delta S also needs to be kilojoules rather than joules. So that number that we had for delta S, minus 200 joules per Kelvin per mole, we've got to divide it by 1,000 and get minus 0.2 kilojoules per Kelvin per mole. And then we can put that number in there. The other thing we've got to be careful about is that negative sign. So it's minus 298 times minus 0.2, and that's equal to minus 92. And remember, if you multiply a minus times a minus, you get a plus. So it's minus 92 plus 298 times 0.2. Okay, so be very careful when you have negative entropy changes, because if you subtract a negative number, that's equivalent to adding a positive number. And if you compute that, you get minus 32.4 kilojoules per mole. And then you actually have to explain what the significance of that is. So don't just leave it at the number. Say, therefore, delta G is negative, and that's what means that the reaction is feasible. Okay, now we've got to explain why it isn't feasible at very high temperatures. And that comes down to looking at this expression again for delta G. Okay, so as the temperature increases, this term becomes more important because T gets bigger. So as T increases, as we go to higher temperature, this term minus T delta S will become more positive, because remember, delta S is a negative number, so minus delta S will be a positive number, and it will get more positive. So minus T delta S becomes more positive. And eventually, it will outweigh the negative value of delta H. So eventually, it will outweigh the negative delta H, so that when you compute that sum, you get a smaller negative number plus a bigger positive number, and so delta G becomes positive, and therefore the reaction stops being feasible. So again, the thing with that is that it's quite easy to sort of see it, but it's not that easy to put it into words, so make sure you've explained it clearly in that sort of way, that that term minus T delta S becomes more positive, and if it's sufficiently positive, it will outweigh the negative value of that, so that delta G becomes a positive term, and then the reaction is not feasible. And then we get this question, okay, it seems like it should be feasible at room temperature, so why do we bother heating it up to 400 to 500 degrees C? And the answer, remember, is because it has a high activation energy, and therefore it's too slow at room temperature. Okay, high activation energy, too slow at room temperature, and that's the end of that question.